All right, welcome back again. So we will continue with our discussion regarding lossless compression. And previously we have seen the Huffman coding, which was generating a binary tree in the sense that uh, it produces or generates a set of uniquely decodable codes because naturally it constructs the binary tree, and since it's in the form of combining the least probable leaves first, it constructs longer leaf depths for shorter for smaller probability um, symbols, and for larger probabilities they will be merged later, therefore their codes will be shorter. So short codes for more probable and longer codes for less probable symbols, which is the idea of the Huffman coding. And eventually it generates some nice code that asymptotically approaches to the entropy. So if the entropy of the code is h of s, for example, the calculated entropy, then Huffman code is guaranteed to have an average code length which is greater than or equal to h of s, but less than h of s plus 1. So the average bit rate for the Huffman coding cannot be more than one more than the true entropy, which is a good thing. This is not particularly very efficient for shorter average code lengths, but for larger codes, for larger sources, if h of s is large enough to be in between these two, would correspond to something pretty nice. So that was remembering about what we saw last week, but today we will start with the dual of this Huffman coding, which is also known as the Shannon-Fano coding. That's a dual approach. To Huffman. The Huffman coding was starting from the less probable two symbols and combining. The dual of that, Huffman was this, was starting from here and then combining. The Shannon-Fano coding is doing this. It starts with a combined couple. It may be more than a couple actually, and then split it into two parts. So in that sense, it's like the reverse operation of the Huffman coding. Huffman coding is combining, Shannon-Fano is splitting. So it starts from the root. It does not start from the leaves. Sorry. Instead of leaves, Shannon-Fano starts from the root. Okay. So how does it work? It's quite simple. Let's say that we have, I don't know, 6, 7 symbols, let's assume. Or it may be a good idea to find the same examples as in my notes. That would make more sense. And then split accordingly. So these are 1, 2, 3, 4, 5. Let me also write their corresponding parts, and I will tell you what or how we came up with these numbers. It's for n and space a o r. Sorry, it's not r. It's e f x and then m and then p and then l and then s and then h. So these are our symbols. I don't know how many it made, but they have their corresponding probabilities that is calculated from one sentence. Of course, it's ridiculous. It doesn't make sense. The example is sentence is example of Shannon funnel. This is the sentence that we have, and from there we're just counting. We are calculating the frequencies or the histogram of individual letters. And as you see, the most commonly encountered letter that we have here is N, the letter N, because in Shannon there are three of them, and then in Fano there is one more, so that makes four letters, at least particularly for this sentence. So the letter frequencies are, this one is 4 over 23, by the way. There are a total of 23 characters, so it's 4 over 23 for the probability. Normally, I should write down their probabilities and I will combine their probabilities. But if you are just counting, just let's count the numbers. We don't need to divide by 23 because all of them will be divided by that. And there are three spaces, the blank, between example of and Shannon and funnel. And the number of A is again 3. So which one would be the second and which one would be the third? It's just up to your implementation. But the overall bit rate result will not change. The result will change, but its efficiency will be the same. So it doesn't really matter. And O is also 3 of Shannon and Fano. We encountered 3 times. And then E appears twice, F appears twice, and the rest appear once. So it doesn't really matter which one you put first and which one you put the last. It's wise to start from left to right in the writing manner, and that's essentially how I did for the ordering. Now, if it was the Huffman coding methodology that we apply, then we would start by combining these two, okay, and then make it with a probability of 2 over 23, and we should put it here, and then the rest will be ones, etc. So it would be like this, something like this, if you remember. But now I'm not going to do that. This is not Huffman coding. This is funnel coding. So what I'm going to do is I will count the probabilities from the top segment and the bottom segment and try to find an equal point to cut it into two equally probable parts. Those equally probable parts will be like the first split from the root to the towards two nodes, not two leaves, because they will be further split into two, and it will go on like this. So the total is 23. And how can I split this one? If I add up 4 and 3, it would make 7, and then 3 more would be 10, and then 3 more will be 13. 23 over 2, the half, is 11.1. It's an odd place, right? 11.1 should be the probability that I have to cut as two equally balanced probabilities, but it's not there. We don't have 11.5. We have either 10 or 13, which is equally distant to 11.5, which is half of 23. So you can either choose to cut from here, from 10 or from 13, and it will give you exactly the same bit rate. But it would be a very good exercise for you to further see which one works better. If such equalities hold, it's usually better to have as balanced a tree as possible. By saying balanced, some of them shouldn't be too long, some branches not too long, some branches not too short, but more equal or balanced tree. Because the longer branches, although they correspond to, of course, shortest probability symbols, uh, it requires longer buffers, memory buffers. So their implementation is somewhat more difficult. So for among the equals, people just prefer more balanced and equal tree structures, and that would make it that would help us to choose this one, this cut, because that cut has 4 symbols to the top and 3, 6, 8 symbols to the bottom. Otherwise, it will be 3 and 9 split, which is more unbalanced. This is a little bit more balanced because I will cut them further. Okay, let's cut it then from here. When we do that, we call the top, we give the top a symbol name and the bottom another symbol name. It can be, the top could be 0, the bottom could be 1, or vice versa. It doesn't really matter. Just 0 for one and 1 for the other. Now, this is the root split branch, which is telling us that the symbols corresponding to N, blank, A, and O will start by 0, and all the others will start by 1. Then we will proceed in a similar manner. We will continue splitting each already split segments. For example, in the next stage, let's use the blue. We will, of course, split from here for the probability distribution of 7 and 6. 7 is close to 6, so this is like the midpoint. For the other, it was 10, so we have to cut from 5, I guess, right? And 5 would correspond to this point. All right. I have to make this line a little bit longer and these lines a little bit longer too, because I will continue splitting. So after this split, the top portion of this portion will be notated by 0 because I'm assigning zeros to the top parts. Sorry. And 1 to the bottom parts. And this top will be 0. This bottom part will be 1. So I split more. And then I will split further. Let me continue with this green color. Clearly, it will be like this, where the top will be only one item with 0 and bottom will be only one item with 1. Why? Because now we have only among 4 and 3. There are 2 items anyway, so strictly when I want to split, it will be split into two. There's no other way. 0 and 1. And this one, the one that we have here, 2, 2, 1, which makes 5, and its split is 2.5, 2.5. So I will split from this 2 place, like this. This will be 0, and the bottom will be 1, because there are 2 symbols inside it, so I will have to split them even further. And let me split the rest 5 again from 2. It could be, there is an alternative to that, but this is also an equal alternative. The top 2 will have a suffix of prefix of 0, and the last 3 will have a prefix of 1, like this. And the top ones are now complete. We don't have to split any further, but the others still have some splitting. So let me use another color. I don't know, maybe this purple-like thing. I split this F and X into 2 by saying 0 and 1. And this M and P will be split from this 0 prefix to 0 and 1. And I will unfortunately split this L, S, and H, these last 3, into 2, like maybe 0 here and 1 for the last 2, and those last will be finally split into 0 and 1, like this. So N will have this symbol, code word, which is starting from the root and splitting into the 0. So the first is 0, and then 0, and then 0. 0, 0, 0 will be N with length 3. Blank will be 0, 0, 1, because as you see, it's 0, 0, 0, and then 1 from the root. So this is the root, okay? As you see, we have also constructed some tree structure. And the next is A. A is, let us see, it is 0, 1, 0, and O is 0, 1, 1. 0, 1, 0, and O is 0, 1, 1. The next is starting with the prefix of 1, for example, E. What is E? It is 1, 0, and 0. Okay, that's it. It does not split any further. It stops there. 1, 0, 0. And then F is 1, 0, 1, 0. That's interesting, isn't it? 1, 0, and 1 and 0. Only then it corresponds to F. So its length is different. It's longer. 1, 0, 1, 0. X is 1, 0, 1, 1. M, let's look. M is 1, and then again another 1 and 0, 0. P is 1, 1, 0, 1. L is 1, 1, 1, 0. S is 1, 1, 1, 1, 0. And H is sorry, H is 1, 1, 1, 1, and 1. So these are the code words that we come up with. As you see, the less frequent ones have longer code words, and the more frequent ones have shorter code words. It's constructed from the root by splitting, and it makes quite a nice code word ensemble, a code book, we can say. And this code book is uniquely decodable. All the code words in the code book are uniquely decodable. No matter how you shuffle these symbols of 3, 4, and 5 long bit sequences, no matter how you put them, you will be able to decode them in a unique manner because it's in the form of a binary tree, and these are the leaves of that binary tree, and therefore it's uniquely decodable. Okay, up to now, do you have any questions? Because these two, the Huffman and the Shannon-Fano coding structures are the two fundamental optimization approaches to construction of efficient binary trees. And Shannon-Fano is also equally efficient as Huffman coding in the sense that the average code word length will be greater than or equal to h of s and less than or equal to h of s plus 1 again. If you have any questions, you can open the mic and contact me. Otherwise, I will just assume that um, it is well understood, I guess. Now, these are construction of binary trees according to a distribution, a probability distribution of symbols. Usually those probability distributions are just calculated from sample data, or sometimes they are given. For instance, if you want to use the English alphabet, of course, it's never uh, efficient for you to look at all the books in the English language and look at their probabilities. These probabilities from all the books, from the works of William Shakespeare to Charles Dickens to all the moderns, the number of frequencies of these letters are very well known, and they are already calculated, so you can use them. But for other things, of course, you have to just calculate from sample data. An interesting place where, for example, Huffman coding is occasionally used, especially in the free and open software implementations of the image compression technique known as JPEG. At the end of the stage, as we know, the most of the compression schemes first makes a transformation, and then makes a quantization, and then finally makes this kind of a lossless entropy coding. So the entropy coding stage of JPEG for image compression uses Huffman coding. And sometimes they give options of optimize for the image and use the standard while saving as JPEG. I'm not talking about a quality setting which changes the quantization ratios. If you quantize more, of course, it will be a smaller file with more distortion. But this one is not what I'm talking about. This one is regarding another optimization. And then that optimization is by just looking at the final code words and taking a look at their histograms, the frequency of the symbols, and more frequent symbols are expressed with shorter bit streams. So the Huffman coding table, this code word that you see on the screen, it can be optimized according to your particular image. First it is transformed, then quantized, then we have the symbols, and those symbols are used for constructing a Huffman table. If you use that constructed Huffman table, it is called an optimization. But if you don't use it, you may still use the Huffman table that is an average and overall good performing half-moon table that has been optimized by the JPEG community by considering millions of images. So using millions of images, these probabilities of each symbol in the JPEG is more or less known. And there is a fixed or standard half-moon table that is already used. It's not optimal to your image, but it's optimal on the average. So you may use it. It will be fast. It will be the fastest JPEG saving instance. But if you don't want that, you may optimize it for your image and it will use that one. But of course, that there is a dilemma for that. There is a compromise. And that compromise is, of course, that image will now, in its header part, will have this Huffman table that is incorporated into the file. Because while decoding, the decoder will not know how to decode if the decoder doesn't know this table. If you have this table, you will be able to decode the Huffman encoded file. So this table needs to be transferred to the receiver or written to the file in the form of a header. Okay, so this is what we can say about um, Shannon-Fano coding too. This Shannon-Fano coding is, and Huffman coding, it is generating a tree. There are some techniques which generates a fixed tree in an unbalanced manner, and you can just assign your more frequent ones to the shorter tree branch, and the longer ones can be assigned to less frequent letters. You can also do that. You can start from a fixed generated tree. The Rice and Golomb codes, which we will not cover, by the way, are like that. They are pre-designed trees, and you do not really design the tree. It is there. You just assign your more frequent letter to the shorter one and less frequent letter to the longer paths, and you do it like that. You just make an assignment. It's you can think of it like this. This tree is given to you, and you have these probabilities of these symbols. So what are you going to do? You will be just saying that the first one goes to the shortest, second one goes to the second shortest, third one goes to the third shortest, and that's how you make these assignments, something like that. But of course, the fixed distribution is not like this for the Rice and Golomb codes. They are different. For the curious, you may take a look at it. And by the way, for the first inequality where Huffman and Shannon-Fano codes provide average code lengths within this range, so they are sort of optimal. The proof of this is also very interesting. I think the books that I have mentioned about you will have these proofs, but I'm not sure. I don't really remember right now. But I may ask about the proof of this one in the first midterm take-home examination, for instance. So long regarding the arithmetic, regarding the Shannon type coders. The next type of coder that we will see will be something else. Without giving a break, I will jump into that. Now I will open a new section and give a different name to that. That is arithmetic coding. All right, let's jump inside that one. The arithmetic coding. What is arithmetic coding? It's an encoder that does not generate a tree, but effectively it generates a number. But that the generation of that number in structure is actually creating a tree. Therefore, it's also a binary tree. It's not binary tree anymore. It's actually more than that. The tree branch splitting is having as many branches as the number of symbols that you have. Therefore, usually for finite expressions, it is the most efficient. It is slightly more efficient than Huffman, and because of that slight the higher efficiency, it is actually patented and you cannot use it. Let me not say it like you cannot use it. You can use it, but you cannot use it for the products that you are selling because there's a patent by IBM. But I'm not sure if the patent is still valid or not because it's an old patent. It's almost an ancient. But if IBM is still using it, they may be renewing the patent regarding this. So, for instance, if you write a JPEG encoder and you want to sell that JPEG encoder uh, to someone, it may be to a company or it may be to as individual sales of a software. If you are trying to sell your software that uses arithmetic coding, you cannot do that because it is probably still patented. But you can write the program, use it for yourself, see the result. That's okay. Only making money out of it is illegal. So what is arithmetic coding? It's the construction of a number, as I say, and that number is technically something between 0 and 1. So we have the top corresponding to 1 and the bottom corresponding to 0. Now, it's a good idea to see the way arithmetic coding works on an example instead of trying to explain all these things. Let's assume that we have three symbols. So the example has x1, x2, and x3 as three symbols, where the probabilities are as follows. The probability of x1 is 0.5, x2 probability is 0.3, and x3 probability is 0.2. Of course, combined probabilities must give you 1. Now, we just split this 0, 1 axis into regions which are as wide as their probabilities, as their corresponding probabilities in proportion. For example, half of this will correspond to essentially x1, like this. x1 is here, between 0 and 0.5. It doesn't have to be between 0 and 0.5, but its length must be 0.5 eventually. So why not, I would say 0.5. And then for x2, I have to have a slot corresponding to 0.3. Let me put it here. So this value makes 0.8. So between 0.5 and 0.8, the length is 0.3 and it corresponds to x2. And between 0.8 and 1, it corresponds to x3. Okay. So these are the probability proportions. And then as the symbols arrive, arithmetic coding starts constructing a number. If, for example, it contains only one symbol, if your message contains only one symbol, let's assume that it is x1, then you can say that the transmitted or the representation number is 0.5 because 0.5 is belonging to x1. Anything within this range, any number within this range will represent x1 for a single standalone symbol if your message is one symbol only. So which number would you try to represent or would you try to transmit? It could be 0.3. 0.3 is also within this range. So 0.3 will also be decoded as x1, by the way. But would you transmit 0.3? And I wouldn't if I were using the binary representations of rational numbers or decimal numbers between 0 and 1. You may know what a decimal number, how a decimal number is represented in binary, but if you don't know, let me remind you. After the point, it is 0 point something, right? After the point, we have these not decimals, but binaries, but in the reverse order. So this one would correspond to, if it is 1, for example, it will correspond to 1 over 2. This will be the stage that is corresponding to 1 over 4. This is 1 over 8. This is 1 over 16, etc. So anytime you have a 1 in here, it will be 0. 1 over 2 is 0.5 in a way, so it will correspond to 0.5. And if this is 1 and this is also 1, it is your number is 1 over 2 plus 1 over 4. If this is 1, this is 0, and this is 1, and all the others are 0, then your number is 1 over 2 plus 1 over 8. Okay, that's how you define decimals in binary. Um, not decimals, of course, it's binary. So the easiest number that you can represent for the symbol of x1 is 0.5, which is only consisting of 1 bit. You just put a 1 here for the representation, and you don't use any of the other numbers, binary numbers. You just put a 1. So 1 would correspond to x1. Of course, the others, their representations will be more difficult. You have to combine these numbers to make a representation of x2, which is something between 0.5 and 0.8. So which number would you use that is between 0.5 and 0.8? It is, you cannot use 0.5 because it belongs to x1, the one before that. But you can use, for example, 0.8. If you try to make 0.8 out of these, you notice that it is too long. So 0.8 is not really the optimal. The optimal place within this range is probably 0.75. And 0.75 is actually 1 over 2 plus 1 over 4, right? And for x3, something between 0.8 and 1 is necessary. It will probably be 0.825, which will be, I don't know, some combinations of these, plus 1 over 32, plus 1 over 64. It goes on like that. So you are trying to make a number. If that number is too precise along the process, it will be requiring more and more number of bits. But if it is weak, if it's not too precise, then you can just use fewer bits. So how do we come up with longer and longer bits? We come up with longer and longer bits by making it more and more precise, by incorporating more and more symbols. So it's not your single symbol that you represent the whole sequence with a number which is becoming more and more precise. How? For example, let's use uh, a sequence. Let's assume that the first in the sequence is x1, which tells us that our number will be between 0 and 0.5. But then comes another symbol in our sequence, which is, let's say, x2. So after x1 comes x2. x1, x2 is your new number. So how do we represent it? First of all, since it starts with x1, it is between 0 and 0.5 because it starts with x1. So first we have to decode x1. So the decoding of x1 will ensure us that our eventual higher precision number will be between 0.5 and 0. And the next symbol will have the proportions according to their probabilities. Like this place will correspond to x1, half of it. But the half is now from 0 to 0.25. And if the next is x2, it will be between 0.25 and 0.4. And if it is x3, it will be between 0.4 and 0.5. So if you express a number between 0.4 and 0.5, it will be decoded as x1 first because it's between 0 and 0.5, and then it's between 0.4 and 0.5, which corresponds to the region of x3. So it will be x1 and x3 decoded if your number is in this range. But our encoding says that it is x1 and x2. So our number is between 0.25 and 0.4 within this range. And then comes another symbol, x something. Okay, let us decide it later. But whatever that later thing is, its range will be between 0.25 and 0.4. That's interesting, isn't it? 0.25 and 0.4. Now our range is like this. And in the next symbol, if I use half of it, the first half, which is between 0.25 and 0.325, it will correspond to x1. And if it is between 0.325 and 0.37, it will be x2. If it is between 0.37 and 0.4, it will denote x3. Okay. So now let's say that the next symbol is again x2. And since it is again x2, it will be within this range between the bottom, which corresponds to 0.325, and the top is 0.37. And this mid number is 0.3475, and this number is 0.361. And the next may be, for instance, x3. And let's stop at this point because you know how it grows. So the final place is within this range between 0.361 and 0.37. So this message sequence will have to be represented as a number in this range. If it is x1, x2, x2, and x3. As you see, that range 0.361 and 0.37 is getting narrower and narrower. Therefore, its boundaries are getting more and more precise and accurate, which makes this. Let me show it from another perspective. I will show it from a perspective of decimals because I'm writing the numbers in decimal format. I'm not writing the numbers in binary form. Look at these numbers. For example, look at this 0.5, 0.25, 0.325, and 0.3475. Look at these numbers. As you see, their representations in decimal is becoming longer and longer. Longer and longer. This also happens in binary format too. I mean, the more precise numbers will require more number of bits. So it's binary precision, binary representation precision will also increase, and its representation will be longer and longer. So that's how it works. If we have more and more symbols like x1, then x2, and then x2 and x3, and then another symbol, another symbol, another symbol, each extra symbol will contribute your overall representation to become longer and longer, like this. First could be represented with only one decimal number, which is after the point, it is 5. And then I need one more decimal, it becomes 25. And then I need one more decimal and it becomes 325. And I need one decimal more. Every time I add a new symbol, like this, and then this, and then this, and then this. So arithmetic coding is not finding the symbols for individual or the code words for individual symbols. Let's write it. Arithmetic coding does not find code words for individual symbols. Instead, it generates the whole code for the whole sequence or the message all at once. So the last thing that you come up with is just a number, and depending on where that number corresponds to, which region it corresponds to, you can just decode it. And the decoding is for humans it may be a little bit complicated, but computer wise it's very simple. For example, if you say that your code is within this range, it is 0.365. Okay, suppose that since it belongs to the top, the final top region, it is 0.365. So how do we decode it? We decode it by making the observations. First, we start with the axis between 0 and 1 and see where this falls into. 0.365 is somewhere here, right? So a number in this point between 0 and 0.5. So we decode it as x1. Okay, we decode x1. As soon as we decode it as x1, we have to split the range now between 0 and 0.5 and look at this number where it falls into. 0.365 is not between 0 and 0.25, so it's not x1. The next symbol is not x1, but it's between 0.25 and 0.4. So we decide that the next symbol after x1 is now x2 because it's in this range. So we decode as x2 and we split the range from the starting point to the ending point, from 0.25 here up to 0.4 here. And then look at these ranges for their corresponding representations. 0.365 is not between 0.25 and 0.325, but it's between 0.325 and 0.37. It's in this range. So the next symbol is x2. And then we split this range of x2, which is 0.325, starting from here up to 0.37. And then this number, 0.365, is in this range. So we decode it as x3. That is the place of x3. Now, here is the ambiguous part. You can further split between 0.361 and 0.37, and this 0.365 will correspond to some place. It may be, I don't know, x1 again. I don't know. I didn't check. Then you may continue decoding this one as x1, x2, x2, x3, and then another x1, and then another x2. It actually corresponds to another infinitely or arbitrarily long sequence. It can be decoded like that. So where do we stop the decoding? We stop the decoding according to a handshake with the encoder. We must know where to stop. How many symbols are encoded with this number must be known from the encoder and the decoder side. So, for example, if you are representing the numbers for chunks, symbol chunks of 4 symbols only, up to 4 symbols, then you must stop here. That's where you say that this number actually corresponds to x1, x2, x2, and x3. And that's it. And then you stop. You don't continue decoding further. Usually you don't do it like this, of course, because 4 symbols is too short, but I'm just making an illustration here. So it is usually in practice way longer. And in practice, the number that is chosen for the binary representation is not any number in between this, but the number corresponding to either the bottom side or the top side. You have to decide which one is included um, in the range. One of the regions must be included. One of the boundaries must be included in the region, in other words. And you just choose from the boundary, not anything in between. But sometimes anything in between, the representation of anything in between may be shorter than the boundaries. So you don't really know what is the best or the most efficient, but you can just approximate the case that if these iterations go quite long, the numbers that you will come up with will be so arbitrarily complicated that their representation will not be more efficient in one case than the other case. On the average, their efficiencies will be the same. And notice one other thing. If the probability of x1, if some of the probabilities are larger, they correspond to wider places. So the more you split, since it is wider, the precision will still be corresponding to a relatively wide position at the end place. So the number representation for that wide spot will be probably obtained by using less numbers or less decimals, less binary numbers. But for the less frequent symbols like x3, if you split by x3, 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 and x3, the final thing will be more and more narrow. And since it is too narrow, its representation will require more numbers. That's how you make the balance of using less numbers for more frequent symbols, for the occurrence of more frequent symbols, and more numbers for the occurrence of less frequent symbols, like because they have a narrower portion. Although this example is a little bit counterintuitive in that sense, because as far as I can see, these numbers, in decimal at least, are obtaining longer and longer sequences, whereas this top one, 0.37, is essentially, at least in decimals, shorter than this one. But this is unexpected. Normally, the numbers of these low frequency regions here and here will require more precision, and their representations will be longer and longer, as opposed to the representations of these, which will probably stay shorter. But since this is a very small toy example, you can come up with any kind of a situation. So this is how arithmetic coding works. You can find their implementations on the web. You can find the implementations of Hoffman, Shannon-Fanon, or arithmetic coding on the web. So it won't be difficult for you to play around with these things. because these are very well-known techniques for making compressions. Now again, without a break, unfortunately, because the last thing that I will talk about is an easy thing. I will very briefly mention about run length coding. Or encoding, which is sometimes abbreviated as RLE, run length encoding. And I'm just going to indicate the idea of this. It has nothing to do with individual symbol expression optimizations of Shannon coding, Huffman coding, or arithmetic coding. It is somewhat more similar to arithmetic coding in the sense that it makes a representation of the whole data and not individual symbol generations. But it runs like this. It works like this. For example, if your transmission message is letters R, T, A, 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 S, D, E, 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 and E. The idea of run length encoding is like this. If it is not having any runs of the same symbol, you just represent it by itself. You say R, and then you say T. And then you see that there are 4 of A's, which is a run of A's. And you make a representation with it like you make an escape code. Let's say that the star symbol is the escape code, which is not encountered in your alphabet. So you don't have the symbol. So you're using it here to indicate that something strange is coming. What is that something strange? The first next character is the run, which is or the running character, the length of the run, which is 4, and then A, which says that there are 4 A's coming afterwards, and then S, and then D, and then there are 5 E's coming. So instead of this, you compress it to be like this. This is just an example way of making an implementation. The correct implementations are various. For example, in CompuServe's GIF, which are nowadays mostly used for animated sequence, short animations, like animated GIFs. But the original GIF it was just a simple image format. Graphics interchange format, it corresponds to GIF. And this run length coding is one of the things that they used because mostly cartoon-like images were compressed over there. For example, a cartoon-like image is consisting of a white background and a black circle shape like this. So when you are encoding it, you see that, let's assume that the background is 0. We have zeros here, all zeros with several lines. So you can say that there are, I don't know, maybe 5,000 zeros. So the first 5,000 is represented with an integer, and the next 0 is represented with a byte. So this is an integer, this is a byte, and this is an escape character. You use one escape character, one integer, and one byte to represent all of the things up to, for example, this point, which encounters or hits the foreground image of the black circle. And then there are these many blacks. So you notate them again with another escape code, but maybe a shorter integer, like, I don't know, 22 of ones. and it goes on like this. As you see, if the color homogeneity is a lot, like for cartoon or drawing images, then uh, encoding them using run length coding will be quite an efficient thing. Okay. This is the overall idea of run length encoding. You can extend the run length encoding idea to first grouping the symbols in your message, and then taking a look at how many of those grouped symbols are utilized. For example, if you're having some text document, in that text document, you may want to take a look at the words, isolated words instead of characters. So from characters or letters to words in English. For example, if you say the one that is correct is the last one, you may want to encode this using run length encoding by first grouping, for example, with th, and then how many times it appears, and things like that. You may want to take a look at it in that aspect. But if you start grouping things, that induces another alternative of uh, lossless coding, which are grouped in the form of in the format of a technique called dictionary techniques, which is a new class of techniques that requires attention. So I will end this lecture now, give some break. What time is it? It is 10:34. So let's start at 11 o'clock. Okay, until 11 o'clock, let's give a break. And after the break, we will start with the dictionary techniques and see how they work. Let me give you a hint about that. The dictionary techniques are the techniques that are most commonly used for zipping your files in your computers. So whenever you say zip or rar or whatever, you're actually using a dictionary technique, not a Huffman coding or anything, but you're using the dictionary techniques. So they are very important, they are very efficient, and we will see how they work after the break. So I'm now stopping the recording, and then and the meeting. And we will meet at 11 o'clock, the same place. So see you until then.